Hey everyone, so I'm not going to be in class this week, so we're just going to continue on looking at the derivatives. So first derivatives is what we kind of introduced before the midterm, but we didn't really do any questions with them, so we're going to start looking at them today. So first derivatives is basically looking at the slope at a tangent to a graph. So what we're talking about when we're talking about a tangent is like the straight line where a curve can be found. Okay, so this is our rule here for first derivatives. So it looks really complicated, but it's not actually that complicated. So this is what you guys took down just before the midterm. So if y, okay, so remember sometimes we call y f of x as well. So if f of x or if y equals x to the power of n, so that's just a curved slope, then dy dx is n x to the power of n minus 1. So we've multiplied by the power and then subtracted 1 from the power. Okay, so we're going to try this in question 2 on page 240. Okay, so the reason why I wrote it out like this is because this is exactly how you'll see it on your log tables, page 25. Okay, so let's go to page 240 and try question 2. So question 2, part 1 says y equals x to the power of 3. So we're differentiating with respect to x. Okay, so we're differentiating with respect to x. So here we go. So we're on page 240. Okay, so let's do question 2, part 1 together. So it said y is equal to x cubed. Okay, and remember our rule is y equals x to the power of n such that y differentiated in terms of x, so dy dx, is nx to the power of n minus 1. So here n is 3, so we're going to end up getting dy dx. Okay, well I need to multiply by the power, so I need to multiply by 3x, and then I get 3 minus 1 as the power. Okay, we don't need to write that step if we can see that straight away. It's going to be 3x to the power of 2. So 3x squared is that differentiated. Okay, so I'm going to pause this video, or no, you're going to pause this video now, and I want you to try all the ones on question 2 there. Okay, so just pause this and try all the ones on question 2. Okay, so now I'm guessing you've tried all the ones on question 2. And I'm just going to go on to the next slide and we're going to come back to question 3 then. Okay, so a reminder that anything that you don't get done in class today, you need to finish for homework. Okay, so I'm going to get you guys to be uploading all of this stuff as a scan. Okay, so we said calculus was the study of rates of change. Okay, you don't need to take this down because we already have something very similar to it down. But what we are going to look at is this here. So we had a function here which was just a line. Okay, so my function here was just a line. It was f of x, or y equals 3x plus 1. So when we look at dy dx here, or f prime x, what we see is, okay, so let's go back to my whiteboard and look at what was on that slide there for a second. Okay, so from that slide, we had y is equal to 3x plus 1. Okay, so we want to look at what is essentially the rate of change of this at any point. Now, what we're going to end up getting is that it's just the slope of the function because it's a linear function. Okay, but let's just have a look. So if we were to differentiate this, so I actually have here 3x. If there's no power shown on the x, what's the power? Well, it's 1. And then here, this 1 is a constant. Now, how could I show an x value that I want a power on this x so that it's equal to, it's just going to go to 1. So how could we do that? So if we look at our log tables, we'll actually see that x to the power of 0 is equal to 1. Okay, now I'm going on a bit of a tangent here, but the reason why is because when we want to differentiate this, what we can look at it as is 3x to the power of 1 plus 1x to the power of 0. So 1 is just multiplying by 1, x to the power of 0. And this kind of allows it make more sense to us, because when we multiply here, when we differentiate this part, so when we differentiate 3x to the power of 1, it means we multiply by 1. So dy dx is going to be 3 times 1, so just 3x to the power of 0. Okay, so 1 minus 1 is going to give me 0. And then this part, I have to multiply 0 by 1. So I'm going to multiply 0 by 1 and I get 0. And then I do get x to the power of minus 1. But what's anything multiplied by 0? What's 4 multiplied by 0? What's 7 multiplied by 0? It's always going to give me 0. So when I actually go to solve this out, I'm going to get 3 by x to the power of 0 was just 1. And then here, 0 times this goes to 0. So dy dx here was just 3. Okay? So when we have a linear function, we see that our dy dx is actually just the slope. So if we had gotten the slope of this function, okay, so rise over run, so it went up 3 and across 1, or y2 minus y1 over x2 minus x1, and we used the point here 0, 1 and 1, 4, okay, we would have gotten that it had a slope of 3. The exact same thing that we got when we done it out with differentiation. Okay, so the slope here was rise over run, and when we differentiate it, we got 3 as well. Okay, so now we're going to look at it if it's a quadratic function. So a quadratic function here, so we have f of x is x squared minus x minus 6 is the one that we're going to have here. Okay, so we're just going to plot that. Okay, and now let's look at a few different points. So this is going to have a different value for anywhere that we have a different x value. Okay, but first thing we're going to do is try and differentiate just this. Okay, so f of x is equal to x squared minus x minus 6. So can everyone try and differentiate that now? Okay, so can everyone try and differentiate, I already forgot what it is. F of x is equal to x squared minus x minus 6. Yeah, okay. So what are we going to get for f prime of x? What are we going to get for that? Okay, so we need to, for this first part, so we can color code this if we want. So my first part, so we need to differentiate every part of this. So my first part is x squared. So what's x squared differentiated? So we multiply by the 2, the power. So we get 2x, and then we're going to subtract 1 from the 2. Okay, then my next one is minus x, or minus 1x, if we want to put a 1 in there. Okay, so that's an x by itself, so it's an x to the power of 1. Okay, so when we multiply this 1 by what's on front, we're going to still get minus 1, and we're going to have x to the power of 1 minus 1. And then my last part is minus 6. Okay, so we can say that's minus 6x to the power of 0 if we want. Okay, so anytime we have a constant, guys, it's just going to go to 0. Okay, so it's just going to go to 0. So that's going to end up going to 0 here. So if you're not sure why, go back and look at what I just explained about the linear function and about it going to 0. Okay, what we're doing here is we're saying it's minus 0 times what was there. So minus 0 times 6x, and we're subtracting 1 from the power. Okay, but when we do that out, anything multiplied by 0 is just going to be 0. Okay, so I'm going to have here 2x to the power of 1 minus 1x to the power of 0. Okay, and then that's going to go to 0. Okay, so here, what's this x to the power of 0 the same as? X to the power of 0, anything to the power of 0 is equal to 1. Okay, so you can test that for yourself if you want. You can type into your calculator 7 to the power of 0, you'll get 1. 11 to the power of 0, you'll still get 1. Okay, anything to the power of 0, we get 1. So that's going to be the same as 2x. Okay, I don't need to write down the power of 1, just an x by itself is the same as x to the power of 1 minus 1. Okay, we can say times 1 if we want, where that x to the power of 0 was. So it's just 2x minus 1 is my final answer there. Okay, so that's f prime of x. Now, depending on where we are in the graph, we're going to get a different value for the tangent. Okay, so why is this going to happen? Well, my x value is going to change. So let's look at the tangent here when x is minus 2. Okay, so if x was minus 2, okay, so if we had f prime of x as minus 2, then we're doing the same function as we got up here, but we're filling in minus 2 for x. So it'll be 2 times minus 2 of minus 1. So that's minus 4 minus 1, which is minus 5. Okay, so the tangent at x is minus 2 is minus 5. Okay, so here, this line here has a slope of minus 5. Okay, we could do the same thing as we done before, get the rise over the run. So we could take 2 points like x as minus 2, 0 and x, my xy points as minus 2, 0 and then my point of 0, minus 10. And we could get my slope there as minus 5 as well. Okay, so let's try this now for if x was minus 1. So if x was minus 1, we're going to have a different tangent again. Okay, so my slope has changed again. I'm filling in minus 1 here. Okay, so here where I filled in f prime of minus 2, that's going to be minus 1. Okay, so we're going to have minus 1 where the x was, so we're going to have minus 2 minus 1, which is minus 3. So the slope of this tangent here in blue, okay, is minus 3. So why am I coming up with these x values? That is the tangent where this blue line is the tangent where x was minus 1. It's if you look really closely into that point, that's the slope where that point is, just given as a line. Okay, so we get minus 3. Okay, so can you pause the video now and try just fill in the values ahead of me for x is 0, x is 1, x is 2, x is 3. Okay, so guessing you have that done. Okay, just for your own benefit purely. At 0, we had a slope of minus 1. Then at 1, we had a slope of 1. Then at 2, we had a slope of 3. And at 3, we had a slope of 5. Okay, so... Okay, so... I have no idea. Oh, now what it's doing is just essentially saying, okay, let's plot this line of the derivative of the function. Okay, so it's the way that this is doing it is by plotting the derivatives. So when x is minus 2, dy dx was minus 5. When x is minus 1, dy dx was minus 3. When x was 0, dy dx was minus 1, and so on. Okay, so you can do it like that. This is kind of a really long way to do it out though. We also could have done it out just by looking at quickly derive this function and then plot this line. Okay, so that's what they're plotting here. Okay, so that's the derivative function there in red. Okay. Okay, so what we're going to do now is we're going to go back to page 240, and I'm going to get you guys to do question 3 on page 240 there. Okay, so this one, for each of the following, find ds dt. Okay, so the only thing that they've done different there is like essentially change the function to being called s instead of y. So instead of dy dx, it's ds d, and then we're differentiating it in terms of t. So it's the function s differentiated in terms of t, but it's the exact same situation. Okay, so I'll do 3 part 5. Okay, so just to help us, I'll do 3 part 5. Okay, so it's page 240, and I'm going to do question 3 part 5. So can you try this yourself first, just to see how you're getting on? Okay, so it said s is equal to 1/2 t squared. Okay, and it wants us to find ds dt. Okay, so here I have s, I need to differentiate it in terms of t. Okay, so I have t here being squared. Okay, so I don't really look at this half, that's just a constant in front. Okay, so when I differentiate, I only look at the powers on this letter here, so the t or usually the x. Okay, so ds dt equals, okay, so I have my half there, and then I want to differentiate this t squared. Okay, so t squared, well, I'm going to end up saying that that's 2t, and then I can write in the power of 1 if I want. Okay, but I still have that half there, so I need to multiply the half because the half was multiplying by my t squared. So I'm going to end up getting 1 t to the power of 1, or just t. Okay, so that is the function s differentiated in terms of t, ds dt. Okay, so can you try the other ones from question 3 now, please? Okay, so I'm going to be, so far what I'm looking for is a scan of question 2 fully completed and question 3 fully completed. Okay, the other ones that we're going to do today is questions 4 and 5.